Hi and welcome to this video. In this video it's the start of a new playlist where I will be going through some of the requirements for the new Chemistry 2.1 standard on quantitative analysis. Carry out a practical investigation into a substance present in a consumer product using quantitative analysis. Sorry about the mouthful. Okay, so first off, quantitative analysis is simply determining the quantity of a substance present in a solution. In level 2, that involves a practical technique called a titration, which is probably going to be an acid-base reaction, although it doesn't actually have to be. And it will also involve a series of calculations to work out some information. Now, to start with this, we really need to think about atoms. And in particular, this is the question that I want you to think about. How small is an atom? Now, if you've got a ruler somewhere around you, can I ask you to get it out now? Fantastic. So if you have a look at that ruler, you can see that it's probably marked in millimeters. So it'll have centimeters and then it'll have little 10 lines between a centimeter which mark the millimeters. Now, if you could zoom right into this ruler, okay, so that space between 2 millimeters is now massive. Okay, so you've zoomed right in, you're looking at really tiny, and you're going to put 1,000 marks between those 2 millimeters. Okay, so between those two markings, so between the distance of 1 millimeter, you're going to fit another 1,000 markings in there because you've zoomed in so small. Those markings are a micrometer or micrometer. Okay, so there's 1,000 of them between a millimeter. Now we're going to zoom even further. So we're going to look in so tiny by this stage that we're going to spread that out. So each micrometer is now miles apart, and we're going to put another 1,000 markings between that. So now we've got like 1,000,000 marks between 1 millimeter and 2 millimeters. Each of those little tiny marks is what we call a nanometer. Are you getting a feel for how tiny this is yet? Fantastic. Okay, so in the space between 2 nanometers, you will fit approximately 10 atoms, 8 to 10 atoms, in that incredibly tiny space. All right, picture it for a sec if you can, and it's pretty hard to do, I know. Okay, so an atom typically ranges from sort of 80 to 200 picometers, or around about 0.08 to 0.2 nanometers across. So if you're thinking about that meter ruler that you've got, in that space between 1 millimeter and the next millimeter, there will be somewhere in the vicinity of 10 million atoms. Okay, 10 million atoms in that tiny space. Means in a centimeter you're looking at 100 million atoms. And in a meter you're looking at about 10 billion atoms, just lined up end to end. Okay, but, and here's the thing, the atoms are not all the same size. So when I say that you're going to get fit that, it kind of depends what type of atom you're actually talking about, because they are all different. Every atom is a different size. Well, every different type of element has an atom of a different size, I should say. Different diameters, different masses. The mass of an atom is going to depend on the number of protons and the number of neutrons in the nucleus. And so that will depend on its mass. The diameter of an atom is going to depend on the attraction between the outermost valence electrons and the nucleus. Greater attraction, smaller radius. We're not really worried about the radius or diameter of an atom in this particular topic. We'll save that one for level 3 chemistry. But the mass of an atom is quite important. Okay, so that is dependent on the number of protons and neutrons in the nucleus. But why should you care? Well, we can use some information to count atoms. If we know how much a given number of atoms weighs, if we knew how much 1,000,000 atoms weighs, for example, we could work out how much one atom weighs. Once we know how much one atom weighs, we can work out how many atoms we've got in 5 grams or 10 grams or 500 grams or 20 kilos or whatever, right? But we need to know how much it weighs. We can count atoms by their weight. We can't count them by lining them up and looking at them through a magnifying glass and counting how many we've got. You'd be there till the earth withered and died before you'd gotten very far. But if we know how much they weigh, then we can work out the weight of any number of atoms. Now, why should I care about that? Well, when chemical reactions happen between individual atoms, right? So an atom of sodium reacts with an atom of chlorine to form this ionic compound that we call sodium chloride, right? So if I want this reaction to take place and to use up all of my sodium and all of my chlorine, I need to have the same number of atoms of sodium and the same number of atoms as chlorine. Because the sodium atoms and chlorine atoms are different sizes, because they have different numbers of protons and neutrons in their nuclei, then we need to find a way to count them. I can't just weigh out 10 grams of each because that will give me different numbers of atoms. So to figure out in a reaction how much reactant we need or how much product is going to be formed or whatever, basically to analyze reactions at that particle level, we need to have an idea of how many particles we've got. The number of particles is all going to be determined by weight. And we use this concept called a mole. Okay, like I implied before, different elements have atoms with different numbers of protons and neutrons, and that's going to determine their masses. So hydrogen atoms have 1 proton and usually no neutrons, and so they're not going to weigh very much at all. Oganesson atoms, that's the biggest ones, the newest discovered ones in the periodic table, 118 protons and I don't know how many neutrons, that's going to be the biggest and weigh the most. Okay, so the periodic table gives us some really interesting pieces of information. It tells us how much 1 mole of atoms weighs. A mole of atoms is this ridiculous number, 6.022 times 10 to the power of 23 atoms. It's very useful because when we look on the periodic table and we see that number that you've always been told is the mass number, what that actually tells us is the mass in grams of 1 mole of that element. So if I've got 1 mole of carbon atoms and I look in the periodic table and the number on the periodic table is, for the atomic mass, is 12.01 on the periodic table, that means that 1 mole of carbon atoms weighs 12.01 grams. So what the hell am I talking about with this mole thing? Well, a mole is just a name for a number. And you know lots of numbers that have names. Okay? When we talk about a dozen, it's just a name for the number 12. A mole is just a name for this horrible number, 6.022 times 10 to the power of 23, Avogadro's number. Some of the other videos that I've linked in talk about it as 6 hexillion or 6 sextillion, can't remember. Basically, it's just a really big number. Now, the thing to remember is it's just a way of counting. So if I look at eggs for a sec, because eggs are something we all know. Right, if I have a dozen eggs, I'm always going to have 12 eggs. It doesn't matter what type of eggs they are. So for example, maybe I've got 12 ostrich eggs. Maybe I've got 12 chickens' eggs. Maybe I've got 12 quail's eggs. I've still got a dozen eggs. It's always 12 eggs. But 12 ostrich eggs, that's the black ones on the left-hand side, 12 ostrich eggs are going to weigh a heck of a lot more than 12 quail's eggs. The quail's eggs are the little speckled ones second from the right, right? So it's still 12, they're still eggs, but they're different sizes, different masses. And I think, eggs is an analogy that I really like when we think about moles and atoms because it makes sense. Okay, 12 eggs, different sizes, different masses, but still 12. You can see the same thing when we look at atoms, elements. Each of these beakers contains 1 mole of atoms of a different type. They have different masses and different volumes because they have different densities. So on the left, in that yellowy one, is 1 mole, that is 6.022 times 10 to the power of 23, 1 mole of sulfur atoms, and it weighs 32.066 grams. And you can see there in terms of volume, it's around about 50 mils of volume, 50 cubic centimeters of volume. Beside that, the next beaker is magnesium. That's a mole of magnesium atoms. Weighs 24.9 grams. Right, and so if you look at the other 3 beakers, the next one along is tin, weighs nearly 119 grams. Silicon, about 29 grams. And being held in the hand is copper, which is about 63 grams, 63.5. All of those beakers contain 1 mole of atoms, 6.022 times 10 to the power of 23. Exactly the same number of atoms. You'll see they're different volumes, they are different masses, but they contain the same amount of atoms. This means that if I want to react copper with sulfur to form copper sulfide, for example, I'm going to need to be a bit careful about exactly how much copper and how much sulfur I put in together. I can't just put together equal amounts of them because actually their densities and their masses are different for the same number of atoms. Okay, so that's the key idea around what a mole is. It's just a name for a number that we can use to count atoms. In the next video, I'm going to spend some time explaining how we use moles, and I'll look forward to seeing you there.